Welcome back. So, organic 2, we're going to do the thing. Yeah, I think I got to get up an attendance quiz for this week just so I have something for when they ask if like everyone attended. So I don't like drop people that actually showed up. So I'll try to get that up by Wednesday and have it up Wednesday through Friday. Uh, it'll be easy. Probably something along the lines of, were you here? So, we are just going to pick up from like we never stopped. So, we're going to start talking about compounds with multiple functional groups. So, in organic 1, we did our best to make sure that all of our compounds only ever had one functional group, right? It was an alcohol, it was an amine, it was an alkene or an alkyne, but we didn't have an alcohol and an alkene in the same molecule. So, man, the clicking. All right, so we're going to start with the kind of the easiest thing, which is going to be hydrocarbons. Right? And so these can have, you can look at hydrocarbons as having multiple double bonds. So you can have 2 olefins. That's called a diene. 3 olefins. Triene. 4 olefins. Tetraene. Right? So I'll give you some examples, but it's pretty easy, right? If a molecule has 2 double bonds, it's a diene, 3 double bonds, triene, 4 double bonds, tetraene, so on and so forth. We're probably going to stop at 4, just to make life easier. Right? It doesn't matter how they're arranged, right? You could have this, right? These are both, right? They both go in the big bucket that is diene, right? Because they have 2 double bonds. Di for 2, ene for double bond. Triene, again, it doesn't matter kind of how they're arranged, just as long as there are 3 double bonds in the molecule, it's a triene. Right? Now, we can kind of categorize the different types of dienes and trienes and tetraenes, right? So we're going to talk about types of polyenes. Right, so polyene is just poly for more than one, right? Multiple double bonds. And these are classified and these are going to be classified based on how close the olefins are to each other. We have kind of the simplest type, which are isolated double bonds. And isolated double bonds are too far apart to interact. So if there's more than one single bond between your double bonds, they are isolated. So here I've got 1, 2, 3 single bonds between those 2 double bonds. The double bond on the left has no idea that the double bond on the right exists. Right? They are too far apart. They don't know about each other. It's like penguins on the North Pole here, and it's nice down on the South Pole. There are no penguins on the North Pole.
I was just asked to real quick redefine what it's meant to be isolated.
If there's more than one single bond between them, then they're isolated. Exactly. So if the double bond was where 2 is, it gets a different name, and they would interact. They would know that each other was there. Right? So if there's right, again, this is an isolated, or these are isolated, right? They are too far apart to talk. The next type of double bond, or diene, the next type of like polyene, these are going to be close enough that they interact, right? So these are conjugated. So conjugated double bonds, they interact via resonance. So they have resonance. The electrons can move back and forth between them. And there's only one single bond between the two double bonds, or between the double bonds. So you've got, this is a conjugated diene, right? It's double bond, single bond, double bond. Right? You can build this out longer. All those double bonds are conjugated, right? There's only one single bond in between each of them. Okay, so that whole system is conjugated. So when I say they have resonance, right? If you remember resonance, it's where pi electrons are able to kind of move back and forth and kind of make an average structure. So I could have a resonance structure where, right, the electrons leave this carbon and go to this carbon. So if I go 1, 2, 3, 4, right, my electrons move, right? I can kind of have a positive end and a negative end. Now, since this is symmetrical, they can also just as easily move the other way, right? Right. But those electrons are able to move back and forth. The electrons between carbon 1 and 2, they talk to the electrons on carbons that are in the double bond between carbon 3 and 4, right? They're close enough that they can interact, they can talk. When they're isolated, they're too far apart, they don't talk to each other, there's no interaction. When there's only one single bond between them, they're conjugated and they're able to move back and forth. Those pi electrons are able to move back and forth. Right? And now the last type is a little more kind of niche or unique. It's cumulated. In accumulated double bonds, the double bonds share a carbon. Even though they share a carbon, there's no resonance. So what these look like is, if you have a carbon, a double bond, a dot, and another double bond, that dot is a carbon. So it's kind of like drawing it like this: double bond, C, double bond. If you don't put a dot or a C there, it just looks like you drew one really long double bond, right? So you have to have something in there to kind of denote that there is a carbon there, right? So it just looks like you went like, I'm drawing a super long double bond, right? If you don't have anything in there, is that accumulated double bond or accumulated diene? Or is it just one long double bond? Right? You give it the dot, then you know. Right? Now, these are as close together as they can possibly be, right? So you would think they would talk to each other. But the way resonance works, right, is the orbitals that the electrons are in have to line up, right? And when you look at accumulated double bond, what happens is, if you remember a double bond, right, you've got your sigma bond, right, your single bond, and then you have your two p orbitals, and your p orbitals have to overlap, right? And that overlap makes your double bond, right? To be accumulated double bond or accumulated diene, to share that carbon, what happens is one of your sets of p orbitals is in the plane of your screen or the board, right? And the other set of p orbitals that makes the other double bond is perpendicular to that. So they stick kind of straight out at you and straight back. So they're at a 90-degree angle from each other. So it'd be like if you made a cross with your arms, right? Right? Your vertical arm doesn't know the horizontal arm is there. That's what's happening with the electrons, right? Electrons, if they're 90 degrees from each other, can't see each other. Something quantum mechanics, math, right? So in accumulated double bond, even though they're sharing a carbon, those two orbitals, those orbitals that the pi bond electrons are in, don't line up. And since they don't line up, they can't talk to each other, right? So my red electrons, they don't know the blue electrons are there because they're 90 degrees from each other. So for us to have something that's conjugated, one of the things that has to happen, right? So see, right? Your orbitals have to line up. So when we have a diene that we draw as being conjugated, right, or saying, oh, this is conjugated, we are just assuming that those orbitals are lined up with each other. And for most simple things, they do line up, right? But when they don't line up, you don't have resonance. So we've got these three types of polyenes, right? Isolated, conjugated, and cumulated. Let's talk about stability. Right? So our most stable type of polyene would be conjugated. Right? That makes sense because the resonance gives you stability, right? The more resonance structures you can draw for a molecule, the more stable that molecule is going to be, right? So when you're conjugated, you have more resonance structures because your double bonds can talk to each other and make resonance structures, right? Next is isolated, right? So there's nothing particularly destabilizing about just having 2 or 3 or 4 double bonds just hanging out in the molecule, not talking or interacting. That's fine. They're isolated. There's nothing bad about them. And then the last is cumulated. And cumulated double bonds are the least stable. And that's because of that central carbon, right? So this carbon right here is strained, right? It's kind of being asked to, like, it's getting pulled in two different directions at the same time. It's like, hey, make a double bond over here and over here. So there is some strain inherent with that central carbon having two double bonds, and that strain leads to cumulated double bonds being less stable than isolated double. Fun fact: space is full of cumulated double bonds, like long chains. How do I know this? Because a guy I worked with in grad school, that's what he got his PhD in. He would make environments in the lab similar to that of space, high vacuum, low temperature, and then would measure the spectroscopic signatures of accumulated molecules and see that they match spectroscopic data from space. So we can infer that these molecules are found in space. My brother's an astronomer, and he talks about complex organic molecules that they see in like stars and stuff. And he's like, "There's benzene." I'm like, "Get out of here with this complex garbage. 6 carbons. Get out of here. Get out of my face with that, man." Like, fine, it's like 85 bajillion miles away. That's cool, but come on, come on. I got a bottle of that in the lab. That's not fancy, man. Okay, so we're gonna talk some nomenclature. Get back on with the easy stuff. All right, so we're gonna start off with like just the polyenes first, right? So let's start out with polyenes for multiple functional groups. So, right, just like when we named stuff before, we're going to replace the Ne at the end of our parent hydrocarbon name with diene, triene, tetraene, depending on how many double bonds we have. So it's a little bit different, right? Where, see, no pressure. What's that? Okay, so 5 carbons. This is, oops, pent, 1ene, or pentene, right? Is how you would say. You're like, oh, it's pentene, right? Here, you took off the ane, right? It went from pentane to pentene. When it's a diene, right, you keep the A of the parent hydrogen. So this is going to be pentadiene. 100%, we're going to get there. We'll get to the numbers. We will do that. All right. So to be officially official, right, we have to number this, right? So this would be, right, you're going to number to give your functional groups the lowest possible number, right? So that means we're going to number in that direction. So this is going to actually be pent to 1, 3 diene, right? So just like when it was dichloro, and you had to put 2 numbers in front of the dichloro, 1 for each chlorine. Same thing here. There's 2 double bonds. You have to put 1 number in front of each they have to put 1 number for each double bond in front of the diene. What's the other thing we're missing? about double bonds. Easy cis trans. Now, when we have multiple double bonds, it's just easier to always just use E and Z, right? So we kind of ditch cis and trans because it looks a little weird if your name is like 3 cis, 5 E, 7 train, like it looks weird. So we just kind of go all E and Z. So like this can just be E penta 1 3 diene. So what's that? 1 2 3 4 5 6 7 8 9. So we're close. Give myself space for numbers. Triene. So we're numbering this way from what I'm hearing in class. 1 2 3 4 5 6 7 8 9. So it's gonna be 1 3 7. Non-triene. Dimethyl. Right, I have 2 methyl groups. We've got a methyl group here and here. So that'll be dimethyl. So 3 7. Oops, myself space for my dash. 3 7 dimethyl. Nana 1 3 7 triene. What else? E or Z? There's 2, right? So the double bond between carbon 3, that has an E or Z conformation. And then the double bond at 7 has an E or Z conformation. So what you do in the parentheses in front is you put the number for the double bond, so in this case 3, and then you figure out if it's E or Z, and you put 3 and then the E or Z, comma, and then 7, and the E or Z associated with that. Did a really good job making a small 3, but a bad 7. Okay, so this double bond between 3 and 4, is that E or is it Z? It's E. So remember what we do? All right, so we take our double bond, we split it in half, and we assign priority to each group on the vinyl carbon. So we're going to look at this carbon here and say what has higher priority, the methyl or the ethylene, or that double bond. And so you're going to go like, okay, carbon, carbon, we can see where it's tied. What's the next thing out here? The hydrogen. We're going to compare a hydrogen to a carbon. The carbon wins, right? Just a longer chain. So this has high priority. Then we look at the other side. Hydrogen versus carbon. Carbon has high priority. They're on opposite sides. So that's E. Then we do the same thing for the double bond that's on carbon 7. Break it in half. This has high priority. That has high priority. Again, they're on opposite sides. So that's E again. So this is 3E7E 37 dimethyl nana 137 triene. Rolls off the tongue. Someone's next child. If Elon Musk can put letters in his child's name that aren't actually letters, we should be fine to do this. You know what's bad? Is when you name your kid the crazy thing after like some fighter jet or some crap, and then they ask you about it and it's the wrong, and you talk about the wrong plane. You've gone too deep. That's what I was trying to say, because he can like buy and sell me like a million times now. Right. Okay. This is your happy reminder that you're not allowed to have forgotten anything from last semester. All of it. All of it. You're from Maryland. Marijuana is not legal there. You have no excuses. If you're from Colorado, I'd be like, all right, you went home and got baked. I understand. But like, it's legal there. But Maryland, it's so slow. Let's name this. It is, the parent hydrocarbon is 7, so we go from here to there. That's 7. That's going to be hexa. Nope. Try again. Hepta. Diene. 1, 5. So again, I set out that we number it this way. And then what are my other substituents? Dibromo, chloro, methyl. Numbers are going to be 1, 2, 3, 4, 5, 6, 7. Right, so it's going to be 1, 1, 4, 5. Right, and if you remember, here we just got lucky that it was like, oh, it's a nice, neat ascending order, right? It's always, you put them in alphabetically, then you give them their numbers. Right, so it just worked out this time it went 1, 4, 5. Like, it could easily been like 5, 1, 4. It doesn't matter. It's how they go alphabetically. So we're going to pretend this is in front. We're going to pretend like I had enough space. All right. Do I need to do E or Z for the double bond on carbon 1? No, because you have 2 of the same group, right? I have 2 bromines. So I can't assign priority. They're always tied. So there's no E or Z there. It doesn't matter. So the first thing that I have to do is I have to assign R or S to carbon 4. Never forget. So let's review. So what has highest priority? So we're going to look at this carbon. What has the highest priority that's bonded directly to that carbon? The chlorine. So chlorine's number 1. Right? Lowest priority, in this case, works out to just be hydrogen. Right? So now I'm going to compare this carbon to this carbon. And if you look at the carbon 3, it's a carbon bonded to 2 hydrogens and then a carbon chain. If you look at carbon 5, it's bonded to a carbon chain and another carbon. So carbon 5 takes priority, right? Because we can hop off the main carbon chain and compare the hydrogen on carbon 3 to the carbon on carbon 5, and we can break our tie immediately. So that'll make the side with the double bond 2, and then this side 3. So that goes clockwise, so that's R. So this is 4R, right? If you remember, when the lower priority group points at you, right? When the lower priority group points away from you, R is, hey now, I thought I turned off my internet. R is, sorry, I follow a button on Twitter, so there you go. So R is clockwise, and S is counterclockwise, right? If 4 is back. If 4 is on a dash, that's how it works out. Right? Now, real quick. I got to assign E or Z to this double bond here. I just redrew it real quick so it's not buried in the million other things we've already drawn on this fourth defenseless molecule. Okay. So if we look at this carbon, this side is going to have priority, right? I'm going to compare a carbon and a carbon. They're going to be tied. I'm going to go out the next atom, which is going to be a hydrogen versus a chlorine. Chlorine wins, gives that side high priority. Now I'm going to look at the other side here. Carbon versus hydrogen. Carbon wins. The two hydrogen groups are on the same side. So this is going to be 5Z. As far as so good? All right, so let's do some things that aren't just dienes, right? So the first thing you want to do is you want to find the longest chain that has both functional groups. I'm going to try to make that just be the longest chain, right? But it just makes it way easier to number if your longest chain has both functional groups in it, right? Because you don't know, because if you don't, brackets become involved, and brackets are scary. Parentheses are fine, brackets bad, right? So, right, you're going to want to pick this as your longest chain, right? Because it has both of your functional groups. It has your double bond and it has your alcohol. And then second thing is you're going to put all of your suffixes at the end of your molecule. So every suffix that designates a functional group goes on the end of the molecule. Right, so right, so you're going to put all the suffixes you need at the end of your molecule. And just like when hexane was an alcohol and it became hexanol, right? If hexene has an alcohol on it, it becomes hexenol. You drop the E from the end of it, and you add the suffix for your other functional group. So the thing that I drew a second ago, if he remembers it, he does now. Right, this is 1, 2, 3, 4, 5 carbons. Pent. It has a double bond, so it's pentene. And then it has an alcohol, so instead of being pentene with an E on the end, we lose that E and we add an OL for all. So it's pentenol. Not worrying about numbers right now. What would that be? What's a triple bond called? Or what's a triple bond suffix? Ine. And then what's an NH2 suffix? Amine. It's the easy one. The amines are called amines. So this is 3 carbons, right? So this would be propyne. Amine. Those are the numbers. I'll tell you why they're the numbers in a second, but they're the numbers. I promise. Okay, there's like a hierarchy of functional groups. All right. So something that can happen or that you will see, this is the most correct way to do the numbering. But what you'll see sometimes is, like for this, you'll see 4 pentene 1 all, where the 4 is referring to the first functional group suffix after the parent hydrocarbon name. So you'll see that sometimes, especially like on older bottles, where that number will be out in front of the parent hydrocarbon name, and it's referring to that first suffix after the parent hydrocarbon. So it's just kind of moving this number to the front. Right, so I'm going to do this next slide a little out of order. All right, so right, what I'm going to kind of lay out here is the order that we number functional groups in, kind of broadly. So things that have carbonyls, things that have C double bond O, if there's a tie, right, these take priority. These are going to get the lowest number in your molecule, right? Then next up, the next most important functional group in terms of numbering are alcohols. Then you have amines. Then you have double bonds. And these are roughly the same as triple bonds. Right, so the roughly the same, right? There is no like, oh, always make sure your alkene has a lower number than your alkyne. When you have a molecule that has both, right, you number to just put the lowest possible number in your molecule. Right, so here, this would be 1, 2, 3, 4, 5, 6. So this would be hex. Oops. Ene. Ine. Give it my E there. And this would be 1, 2, 3, 4. 1 hex 1 ene 4 ine. Right? But I could easily just kind of turn this around. And I wouldn't number it. Here I would just go like, okay, now the lowest possible number I put in my molecule is 1 if my alkyne is 1. So I'm going to make the alkyne 1. There's no difference. So you're basically treating the alkene and the alkyne both like they're double bonds. You're saying, well, okay, which one puts the lowest possible number in my name? So you're going to say, okay, this is going to be perfect. Hex 4 ene 1 ine. It doesn't really matter. You just kind of switch back and forth.
I get asked why it was een then ein and not ein then een.
I'll be 100% honest. It's like this because I know it sounds right, but I don't know the exact rule. So I'm just that's the way every molecule I've heard like this is named. So I'm like, this is the right way, but I don't know 100% why. So I'm sorry. I'm a failure. So like for this, right, either direction I number, the lowest number I get is 2, but alcohols are more important, right? So I'm going to number to give the alcohol the lower number. So I'm going to number in this direction because that gives my alcohol the lowest number. So this will be 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. Hepene all. So this is going to be 2, 5. Now here there's only one double bond. So I can just say this is trans, right? But if I start having multiple double bonds and I start having parentheses where I have E's and Z's, R's and S's, it's just best to stick with E's and Z's. Make sense? Right, the alcohol is just more important. For this joke to work, you have to know that ketones are ones. Old MacDonald had a molecule. Een ein own. I learned it roughly 1999 from my organic chemistry professor, and now I give it to you. I pay it forward through the generations. So now you know about Old MacDonald's molecule, een ein own.